So, problem 5.1 is shown on the screen. We see a block diagram with a feedback loop, and this dotted block is called G of S in this block diagram, and let's call this other dotted block G tilde of S. So what we have is G of S something like this, and the input is given to be 0. Now the first question is to calculate the open loop transfer function from y to v, that is to calculate G tilde of S. The second question is to find the state space model of the closed loop system, which would then be an autonomous system because the input is set to 0. Now before we just simply start calculating the transfer function, I would like to motivate this problem. So this problem is related to the Hamiltonian system that we defined as a replacement for solving the Riccati differential equation. So maybe it wouldn't harm to quickly recap where this lies in the big picture. Remember, we are trying to solve this LQR problem subject to so that's our key control problem. We call it the LQR problem, linear quadratic regulator problem. We saw that we could solve this problem by solving Riccati differential equation with this boundary condition. And once we have a solution to the Riccati differential equation, u star of t equal to minus R inverse P transpose P of t x of t. This u happens to be the solution to the LQR problem. Now we also see that this is a nonlinear differential equation due to the product, due to this quadratic term in P. So we posed another problem, or rather a fictitious system of this form. So this is now a system of linear differential equations, and if we could solve this system of linear differential equations, we observed that P of t given by y of t x of t inverse solves the Riccati differential equation, and therefore u star of t equal to minus r inverse p transposed t x of t inverse solves the LQR problem. This times x of t, of course. Yeah, now what we want to do in this problem, this seems completely unrelated to the current problem, but what we want to achieve with this problem is to understand or give an interpretation to this system. We will see shortly how to do that. So now with this sort of preface in mind, we can try to solve part A, which is to find the open loop transfer function from y to v, that is what we called g tilde of s, this block. Now yeah, we just take a snapshot of this. Here so we can see now that lambda dot is minus A transpose lambda, so this is y, minus C transpose y, and V is minus P transpose lambda. So we already have a state space representation for G tilde of S. And we know that the transfer function representation for G tilde of S is then just minus P transposed times Si minus A transposed inverse minus C transposed. So this comes from the fact that if we had a state space model like this, the transfer function representation is given by this expression here, and you can try to prove this by taking the Laplace transform of both sides on this equation and then algebraically manipulating to obtain the transfer function as shown here. So now let's sort of make this a bit cleaner. So the negative signs get cancelled, we get P transposed. You can take this negative sign gets cancelled, so we get Si plus A transposed inverse C transposed. So this is G tilde of S. Now note that Note in this figure, the G of S is the standard state space model with the usual notation. So what I mean is this thing is basically G of S. So let me just write down here, that is C into Si minus A inverse P. That's G. And now the question is to see how these two are related. Now first observe that G of minus S is equal to C times Si minus Si minus A inverse P. So we replace S by minus S and we can pull out the sign now. So we get minus C into Si plus A inverse P. Now if we take the transpose of this, G of minus S transposed would be minus P transposed times Si plus A inverse transposed times C transposed. What we have used here is AB transposed is P transposed A transposed. Now this is nothing but minus P transposed times Si plus A transposed inverse C transposed. What we have used here is A transposed inverse is A inverse transpose. And I think we also used this in one of our previous exercise problems. And you can try to prove this as well. So now we recognize that this thing is our G tilde of S. So what we obtain is G of minus S transposed is minus G tilde of S. Well, what does that mean? Let's think of the scalar case for simplicity, and you can try to work it out for the vector valued case later. So for the scalar case, let's write this as a numerator polynomial over denominator polynomial. Now similarly, so what we would now have is G tilde of S is minus G of minus S. So the transpose will go away because now we are in the scalar regime. What this means is that it's nothing but minus n of minus S over d of minus S. So that is our G tilde of S. When G of S is n of S over d of S. So if S equal to S1 is a pole of G of S, we would have that d of S1 will be 0. Now let's see what kind of poles we can obtain for G tilde of S. So for S equal to S2 to be a pole of G tilde of S, we need D of minus S, D of minus S2 to be equal to 0. So that would mean minus S2 is a pole of G of S. So what we have is the following result. If S1 is a pole of G of S, minus S1 is a pole of G tilde of S, and we also have the other way around. Now it's still not yet clear how this is related to the Hamiltonian system that we defined as a replacement for the Riccati differential equation problem. So that will be eliminated in part B. Now we need to find the closed loop dynamics of the block diagrams. So let's write down the differential equations first. And we additionally have V times R inverse V is U. So if we write down now the closed loop dynamics, we obtain x dot is AX plus BU, but U is R inverse V, so BR inverse V, but V is minus P transpose lambda. Similarly, lambda dot is minus A transpose lambda minus C transpose Y, but Y is Cx. So if we write this in the matrix form, A transpose minus C transpose C and minus A transpose X and lambda. So what we have is that this block diagram indeed represents the Hamiltonian system.